Welcome to the lecture series on numerical methods. Last class we have discussed this interpolation on finite difference operators. So, in the finite difference operators, first we have started about this Newton's forward difference operator, like delta operators, Nabla operator, then this central difference operators and average operators. So, this finite difference operators, whatever we have discussed, that includes like Nabla, delta, and this central difference operator delta and the average operator mu. And in this presentation, first I will just give a few introduction about this few operators that I have discussed in the last class. Then we will just go for Newton's forward difference formula and Newton's backward difference formula, and then the error approximations. So, this forward difference operator, backward difference operators, whatever it is operated in the last lecture, that are basically expressed in the form of Nabla of f of x, that is represented as f of x minus f of x minus h, and delta of f of x, it is expressed in the form of f of x plus h minus f of x, and this central difference operator delta of f of x, it is expressed in the form of f of x plus h by 2 minus f of x minus h by 2, and this average operator, this is expressed in the form of half of f of x plus h by 2 plus f of x minus h by 2. So, whenever we will go for this application of this 4 difference operators, so then we have to go for the shift operator and differential operator here. Basically, if we are just using sequentially these operators, so sequentially this can be applied, like if Nabla of y1 can be applied, so it can be written in the form of y1 minus y0 here. So, then Nabla of y2 can be written as y2 minus y1. So, likewise we can just write Nabla of yn can be written as yn minus yn minus 1. Similarly, if we will just apply this forward difference operator sequentially, so delta of y0, this can be written as y1 minus y0, delta of y1 can be written as y2 minus y1. So, likewise if you will just express delta of yn minus 1 can be written as yn minus 1. So, similarly we can just use for central difference operators like delta of yr, if you will just write, this can be written as y of r plus half minus y of r minus half here. Similarly, if you will just use this operator in a average operator form, so this can be expressed in the form of mu of yr, this can be written in the form of half of yr plus half plus y of r minus half here. And if we are just using these operators in a shift operator form, usually E is called the shift operator here. So, usually this shift operator is denoted in the form of E, and it can be written in the form of E of f of x as f of x plus h here. Similarly, if we will just write a differential operator, so this differential operator is signified as capital D here, and if it is operated on f of x here, that can be written as d by dx of f of x. So, if we want to extend these operations in different forms, like how we can express this delta operator, Nabla operator, or this central difference operator, or this average operator in shift operator form, then we have to expand these operators in different forms. So, first if you will just express this shift operator in a recursive way, so we can just write E of f of x as f of x plus h, then E of f of x plus h as f of x plus 2h there. So, if you will just express f of x plus h in a Taylor series expansion form, then we can write this Taylor series expansion as, that is basically if we are just writing E as a shift operator here, it can be expressed in the form of f of x plus h here. So, then sequentially if you will just use E of f of x here, so it can be expressed as E of f of x plus h, and this can be written as f of x plus 2h here. So similarly, if we will just use like a delta of f of x here, so it can be written in the form of f of x plus h minus f of x is this one. So it can be written as e of f of x minus f of x here, and which can be written as e minus 1 into f of x. Similarly, we can express nabla operator in the form of shift operator here. So that is basically written in the form of like nabla of f of x here as f of x minus f of x minus h. Since we are just writing e of f of x in this form here, so that is why it can be written as e of f of x as e raised power 2 f of x here. So this means that this can be written as f of x plus 2h here. If we want to write f of x minus h, then it can be written in the form of e of minus 1 of f of x here. So similarly, we can express this expansion here as f of x minus e power of minus 1 of f of x, which can be written as f of x, or we can just write this one as 1 minus e inverse, that is as the operator here operated on function f of x here. So different operators like central difference operators also we can just express, that is in the form of e to the power half minus e to the power minus half. Since we are expressing this central difference operator, that is the delta of f of x, usually it is written as f of x plus h by 2 minus f of x minus h by 2. So which can be written as delta of f of x as f of x plus h by 2 minus f of x minus h by 2, and this can be written as e power of half f of x minus e power of minus half of f of x, which can be written as e power half minus e power minus half of f of x here. So obviously we can just write the operator as delta equals to e to the power half minus e to the power minus half here. Similarly, the average operator, it can be expressed in the form of mu of f of x as half of f of x plus h by 2 plus f of x minus h by 2, and this can be expressed as a half of e power of half plus e power of minus half operated on f of x, and hence we can just express mu as a half of e power of half here plus e power of minus half here. So sequentially, if we will just apply this shift operator, then we can express delta plus 1 equals to e equals to 1 plus del square by 2 plus delta square root of 1 plus del square by 4 also. So it can be obtained from this operator here, since usually we are just expressing delta as e raised power half minus e raised power minus half here. If we will take square on both the sides, then we can express that as, since we are just expressing delta as e power of half minus e power of minus half here. So that is why we can just express del square as e plus e raised power minus 1 minus 2 here, and which can be expressed in the form of e plus 1 by e minus 2, and which can be written as e square plus 1 minus 2e by e here. And in a product form, if you will just write, this can be expressed as e square minus 2e minus del square of e plus 1 equals to 0 here, and this implies that it can be written as e square minus e into 2 plus del square plus 1, this equals to 0. If we want to find this root here, that is as e can be written in the form of that as 1 plus del square by 2 plus delta square root of 1 plus del square by 4. So this is the formulation usually we are just obtaining here, that is e in the form of central difference operators. So if we want to express this one E as in the form of a forward difference operator here, so E is usually written as 1 plus delta also. Since we are just writing delta of f of x as E of f of x minus f of x here, which can be expressed as E minus 1 of f of x, and this implies that delta can be expressed as E minus 1. This implies E equals to 1 plus delta here. So directly if you want to find this root here, we can just write this one as a minus b plus or minus square root of v square minus 4ac square root by 2a. So here a is 1 here, and the coefficient minus b means this is b coefficient is 2 plus delta square, and c is 1. So that is why this is the root for this equation here. Next, if we want to express this delta in the form of a average operator here, we can just express here the average operator as mu equals to half of e power of half plus e of minus half here. And if we take square at both the sides, so it can be expressed as mu square equals to 1 by 4. This can be expressed as e plus e power minus 1 plus 2 here. Since already we have known that e plus e inverse, it can be written as here, if you will just see, this can be written as delta square plus 2 here. So I can just write this one as 1 by 4 del square plus 2 here. And if I want to find this square root of this mu function, so it can be written in the form of like mu equals to, that is expressed here also, that is in the form of like plus or minus 1 by 2 square root of del square plus 4 here. So usually it is just written in the form of like if you will just write inside this function here, that can be written in the form of del square by 4 plus or minus here, so plus 1 here. So this is the expression that is written in the form of mu as in the form of delta here. So next, if we want to express this shift operator in the form of a differential operator here, so usually E of f of x is written in the form of f of x plus h, and hence if you will just expand in Taylor series form here, that can be written as f of x plus h f dash x plus h square by factorial 2 f double dash of x plus this one. So we can just write this one as, since f dash x is written in the form of here h d of f of x, h square by 2 factorial d square of f of x here. So we can express this as e raise h d operated on f of x. So directly we can just write e as e to the power h d here. So specifically if we are just expressing this one, this shift operator in the form of differential operators here, then we can express this central difference operator delta as e to the power half minus e to the power minus half, which can be written as e to the power h d by 2 minus e to the power minus h d by 2, which can be written as 2 sine hyperbolic h d by 2 here. Similarly, if we will just write average operator here mu, this can be written as e to the power half plus e to the power minus half by 2, which can be written as e to the power h d by 2 plus e to the power minus h d by 2 and divided by 2 here, and this can be written as, I think, cos hyperbolic h d by 2 here. Since usually it is just expressed in the form of half here, so that is why half is coming over there. So this half will cancel here, so cos hyperbolic h d by 2 here. So next we will just go for this interrelation between different operators here. So, that is E as expressed as in the form of delta, in the form of nabla, in the form of a central difference operator delta, and then it can expressed in the form of differential operators. So, all of these operators we want to express in different forms, that is E, delta, nabla, and the central difference operator small delta, then mu is the average operator, then the differential operators here. So, then we will just go for this polynomial approximation in differential operators. How we can use these differential operators in a differential form also there. This means that how we can use this forward difference operators like your delta, nabla in a differential sense for a polynomial here. So, if suppose we are just considering f of x is a polynomial here, first we will assume f of x is a constant polynomial. Suppose if f of x is a constant polynomial, we can write f of x equals to a here. So, if I am just writing this polynomial f of x as a constant polynomial here, then I can apply here this forward difference operator del of f of x can be written as f of x plus h minus f of x here, which can be written as a minus a, this equals to 0 here. So, next if I am just expressing f of x equals to ax, that is a polynomial of degree 1 here, then delta of f of x we can just write as f of x plus h minus f of x, and this can be written as, since f of x plus h it can be replaced as a into x plus h here minus ax. So, this can be written as ax plus ah minus ax here, and it can be written as ah here. So, if again we will apply here delta operator, this means that del square of f of x for this function here, we can just express delta of f of x, which can be written as delta of ah, and obviously we have already defined that delta of a constant function, this is just giving you a 0 value. So, it can be expressed as 0 here. Similarly, if you will just consider f of x is a second degree polynomial, that is f of x equals to x square, then delta of f of x, this will just give you a first degree polynomial, and delta square of f of x, that will just give you a constant polynomial there. So, suppose if you are just considering f of x equals to x square here. So, if you will just consider f of x equals to x square here, then delta of f of x can be written as x plus h whole square minus x square here. So, I can just write this one as x square plus 2xh plus h square minus x square, and it can be written as 2xh plus h square here. So, repeatedly if I will just apply one more operator here, this means that delta square of f of x, I can just write delta of f of x, which can be written as delta of 2xh plus h square here. Obviously, already we have defined this one, I can just write h of delta of 2h delta of x here plus delta of h square. So, already we have obtained that delta operated on a constant function, that is just giving you 0 value, then we can just write this one as 2h here, 2h square here, since I have just written delta of x here 2h square, since delta of x can be written as x plus h minus x, this one. So, that is why it can be written as h here. So, the final function is coming as 2h square here. So, if we are just applying this operators on a polynomial, so it is just operated on like 0, 1, 2 degree polynomials. In a generalized form, if we want to express this operator, so there is a theorem for this, and the theorem statement states that the nth difference of f of x equals to x to the power n is n factorial h to the power n here. This means that the statement we can just write it off as the nth difference of f of x equals to x to the power n is n factorial h to the power n here. So, this we can just prove this theorem in the form of induction here, since for n equals to 0 we have already satisfied that one, for n equals to 1 we have satisfied, n equals to 2 in the previous case already we have shown that one. So, if we will just assume that this theorem is true up to n minus 1, this means that 0, 1, 2 up to n minus 1 here, we can just write if f of x equals to x to the power n minus 1, then it can be written as delta to the power n minus 1, f of x can be written as n minus 1 factorial h to the power n minus 1 here. So, first we will assume that the theorem is true for n equals to 0, 1, 2 up to n minus 1 suppose. Then each of these functions, so like f of x equals to x, it can be expressed as your function that is 1 there, that is delta of f of x. If we are just expressing f of x equals to x square, then delta square of f of x can be expressed as 2 there. So, likewise it is just satisfied that this theorem is true for n equals to n minus 1 also there. So, if we will just assume that this theorem is true for 0, 1, 2 up to n minus 1 here, then for del to the power n of f of x, we can just write del to the power n of x to the power n here. So, we can just express this one as del to the power n minus 1 delta of x to the power n here, and this can be written as del to the power n minus 1 of x plus h whole power n minus x to the power n here. And we can just expand this x plus h whole power n in a binomial sense, and if we will just expand this one in a binomial sense here, we can just write del to the power n minus 1 and x to the power n plus n h x to the power n minus 1 plus n into n minus 1 by factorial 2 h square x to the power n minus 2. So, likewise the final is h to the power n minus x to the power n here. So, x to the power n, x to the power n, it can cancel it out, and I can just write del to the power n minus 1 n h x to the power n minus 1 plus n into n minus 1 by factorial 2 h square x to the power n minus 2 plus up to h to the power n. Since already we have assumed that this theorem is true for all the values, that is 0, 1, 2 up to n minus 1, if you will just see here, except this term, all other terms will take 0 values here, since all of these polynomials are degree less than n minus 1 here. So, the final term we can just write as del to the power n minus 1 n h x to the power n minus 1 here, plus all other terms are assumed to be 0. So, in the final form we can just write delta of f of x, that is del to the power n of f of x, that is del to the power n x to the power n, it can be written as del to the power n minus 1 n h x to the power n minus 1 here, and which can be written as n h into n minus 1 factorial h to the power n minus 1. So, it can be written as n factorial h to the power n. Finally, we are just obtaining if f of x is a polynomial of degree n, then we can write del to the power n x to the power n as n factorial h to the power n here. So, next we will just discuss about how we can just use in a tabular form of the forward difference operator, backward difference operator, central difference operators, and average operators here. So, if you will just write these operators in a tabular form, in the forward difference table, if you will just see, we are just moving in the end of the table to the beginning value of the function in a forward difference form. In a backward difference form, we will just move to the value which is existing at the end of the table there. So, if I am just writing this forward difference table, so this forward difference table can be written as if I am just writing here I xi yi here, then I equals to 0, 1, 2, 3, 4 suppose. Then xi values are x0, x1, x2, x3, x4 are the values. Associated these functional values will be y0, y1, y2, y3, y4 here. Then if you will just use this forward difference operator, then delta of yi. So, first two differences, so I can just write delta y0 here, then second one I can just write delta of y1 here, third one I can just write delta of y2 here, and the last one I can just write delta of y3 here. Since difference of these two is just giving you delta y0 here. So, then difference of y2 minus y1 is just providing delta of y1 here. Then difference of y3 minus y2 is providing delta of y2 here. Then difference of y3, y4 minus y3, it is just providing the value of delta of y3 here. Similarly, if you will just go for the second operator here, that is in forward difference form, I can just write the difference of these two, it can be written as delta square of y0 here. Difference of these two can be written as the del square of y1 here. The difference of these two, we can just write delta square of y2 here. Similarly, we can just go delta q of yi here, and where we can just get the difference of these two, it will just give you delta q of y0 here. Difference of these two, it will just give you delta q of y1 here. Again, if you will take the final difference, since we have here existing 5 different points. So, 5 different points means lastly we can just go up to the polynomial of degree 4 here. So, then I can just write the difference of these two can be written as a delta to the power 4 of y0 here. So, in the final form we are just obtaining this value, that if you will just see in the final form, this difference is moving to y0 point in the final form. This means that if a value is existing at the beginning of the table, and if it is asked to evaluate, then we can use this forward difference form to evaluate this value in a differential form there. Then we will just go for the discussion of a backward difference table here. So, if we will just go for backward difference table, the same formulation we will just use, but this will take a step back of the values for each of these calculated value or the calculated tabular points. So, if you will just use this backward difference table here, that is in the form of I equals to 0, 1, 2, 3, 4, and associated tabular values are like xi's, that is x0, x1, x2, x3, x4 here, and associated variable values, that is yi as y0, y1, y2, y3, y4 here. If you will just express these tabular values, then we can just write this as nabla of yi here. So, nabla of yi we can just write here nabla of y1, then difference of y2 minus y1, this will just give you nabla of y2 here. Difference of y3 minus y2, that will just give you nabla of y3 here. Difference of y4 minus y3, this will just give you nabla of y4 here. Similarly, if you will take difference of nablas here, then nabla square of yi I can just write. So, nabla of y2 minus y1, so this will just give you nabla square of y2 here, then nabla square of y3 here, then the difference of nabla of y4 minus nabla of y3, that will just give you nabla square of y4 here. If we will take again the difference of these two here, that is nabla q of yi, I can just write nabla q of y3 here, then the difference of these three, that is nabla q of y4 here. And if I will just write nabla 4 of yi here, then the difference of these two, that will just give you nabla 4 of y4 here. In the final form, if you will just see, this difference is moving towards the end of the tabular value here. This means that if a function is asked to evaluate at the end of the table, we can use this backward difference table to evaluate the values here. So, in the next lecture, we will just continue the central difference operator and average difference operator, and next onwards we will just go for this Newton's forward difference formula and backward difference formula. Thank you for listening this lecture.